Despite what I just said in the previous video about harmonic and holomorphic functions not being the same, sometimes there's properties that are shared by both of them. And one of them is this mean value property. So in order to set this up correctly, I want to remind you of the Cauchy integral formula, which says that under certain assumptions that this integral, 1 over 2 pi I times the integral of f over z minus w is equal to f of w. The conditions here are that f has to be holomorphic on a region G, gamma has to be inside G, gamma has to be piecewise smooth, has to be positively oriented, it has to be closed, and it has to be simple, meaning so simple means that the curve doesn't intersect itself. So that's a curve that's not simple. Oops, here's a curve that is simple, right? It just doesn't self-intersect except at the endpoints. So under those conditions, Cauchy integrals formula is valid. And in particular, if you think about gamma being a circle of radius r, so if this circle of radius r is inside this region G, then we get the following corollary. So 1 over 2 pi times this integral from 0 to 2 pi f of w plus r e to the it dt is equal to f of w. Okay, so that's f of w. Now that's under the condition that f is holomorphic. And again, here gamma is a circle. So just assume that this positively oriented circle lies inside our region G. So if that's true, then this is true. So in particular, this is true for holomorphic functions. This formula is also true for harmonic functions. Okay, so if U is a harmonic function on a region G, and if the region G contains a closed disk centered at W, then this same formula is valid. What I mean by the same formula is that this formula up here is actually true for functions f that are holomorphic. But you can take the real and the imaginary parts together. And this formula is also true for the function u and the function v. And we know that if f is holomorphic, then u and v are harmonic. And so that's going to basically be our proof here, is that this property is shared actually by harmonic functions. We just have to be a little bit careful here. The only thing that we have to be careful of is that we're starting with a region G, and then we're assuming that this region G contains some closed disk centered at W of some radius capital R. Now, if it contains a closed disk, that's fine, but we really need to work over a region. We need to work over a closed, and we need to work over a bounded and open set. And it turns out what you can do is that if you have a region G containing a closed disk, here's a picture. If you have a region G containing a closed disk, you can find an open disk, which is this green dotted area, okay, and all the points inside, of course. But if I color that, then this gets really messy. So I am not going to color the inside. But if you take an open set G that has a closed disk in it, okay, so here's the closed disk, then it turns out that you can always just enlarge it just a little bit so that this enlarged disk is still in G, and the enlarged disk contains the closed disk. Okay, so a little bit of technical stuff here. This is actually left as an exercise in chapter 6. I forget what number, but the idea is pretty straightforward, right? So if you have an open set G, that means that you're not including the boundary. To have a closed disk means that this closed disk can't fit right up against the boundary because the boundary of G is not in the set, so you got to move it just inside. And as soon as you move it just inside, then you can find a little gap between the set G and the closed disk where you can fit a slightly larger open disk that contains the closed disk. Okay, I hope that that was clear enough in words, not in images, but there we go. So here is a result that's actually true for both harmonic and holomorphic functions. Okay, and again, the proof is written out really nicely in the book, but the proof basically relies on all the facts that we've had so far. If f is holomorphic, then its real and imaginary parts are harmonic. And we already know that the statement is true for holomorphic functions. Therefore, by taking the real and the imaginary parts, it's true for harmonic functions as well. That's basically the argument. You have to be a little bit careful that everything works out as far as the right regions that you're talking about, but everything works out fine and the details are in the book. Now, this result is sometimes referred to as the mean value theorem. So this is sometimes called the mean value theorem for the complex numbers, okay? Because it has kind of that flavor of the mean value theorem, okay? So kind of like an integral mean value theorem. All right, so that's the mean value theorem. So it happens to be true for harmonic and holomorphic functions. Sometimes instead of just the mean value theorem for the complex numbers, sometimes this is also called Gauss's mean value theorem. Okay, so if I ever say Gauss's mean value theorem, now you know what I mean. Okay, so Gauss's mean value theorem is just this theorem.